Hey there peeps, this is Rotational Work and Energy, and forgive the white shirt if I blend in and I'm floating head and floating hands. That's just what you get this time. What is rotational work? Well, it's tau times delta theta. Well, there's a bunch of Greek letters. What does that actually mean? It means torque times angular displacement. So if you have a torque and it produces an angular displacement, then rotational work has been done. The unit, just like with linear work, is the joule, okay? What about rotational energy? You'll notice that the format of this relationship here is similar to that of linear kinetic energy. So this rotational kinetic energy essentially is 1/2 I omega squared. The unit is also joules. What is that? As we remember, I is rotational inertia. And it depends on the mass and its distribution of that mass around an axis of rotation. And then it also depends on the angular velocity squared. And so that brings us to the conservation of mechanical energy, meaning that we're not dealing with dissipative forces like friction that create thermal energy. We're just dealing with the mechanical part, and it's the same as it was before, except we have the added term of rotational energy. Let's take a look. E total is constant, so that's still the same before. E naught equals E final. So the energy before is the energy after the whole event. In terms of the concepts, we have gravitational potential energy, kinetic energy, and rotational energy, all naught. And that equals, on the other side of the equation, gravitational potential energy final, kinetic energy final, rotational energy final. Now in terms of the variables themselves, we get mgh, 1/2 mv squared, and 1/2 I omega naught squared, okay? And on the other side, of course, mgh, 1/2 mv squared, and 1/2 I omega squared, all with the final subscript. Okay, to be able to use this, we have to remember a couple things. I depends on the type of object, so we might have to look that up if it's not given. So if it's a cylinder or a sphere or something like that, we'll need to look up the value for I and its relationship. We also want to remember from the Rosetta Stone what omega is. And omega is linear velocity divided by the radius around that axis of rotation. Okay, let's do an example where we compare on an inclined plane. Don't worry, this is actually going to be quite cool. You're going to like energy a lot because it makes things so much simpler if we want to find velocities than the old techniques of trigonometry and whatnot. Okay, so we're going to do an inclined plane. We're going to compare two objects. They are a sliding puck on a frictionless plane and a rolling puck. So here we go, bring it, and now. So here it is, the frictionless incline versus the roll down that same incline. So we're sliding versus rolling, and here we have an object that's a puck. The puck is considered to be a solid cylinder. What's the final velocity? And even though I've drawn everything here, I'm not doing a free body diagram this time. We're going to use energy concepts. They're scalars. Therefore, we are concerned really about the forces acting on it instead of the energy of the system. So I wrote theta here just to indicate that the angle is the same for each of these ramps. Each has the same height, h, and we have a reference line at the very bottom that indicates that the gravitational potential energy is 0 and 0. Okay, the bottom is our reference point, like the ground. All right. We start off with a V naught of 0 meters per second in both cases, okay? So what do we have? Well, let's look at this one up here first, the sliding puck. Okay, with the sliding puck, we have gravitational potential energy, but because we're starting off at V naught equals 0, and it's obviously not rotating if it's sliding, these two guys are 0 in the beginning stage over here. In the final stage, we have no gravitational potential energy because the height is going to be 0 when it reaches this red line over here as it slides down. We have kinetic energy at the end, the energy of motion, linear motion, but we will not have rotational energy in the case of the sliding puck. So what does that look like in terms of the variables? Okay. Well, mgh equals 1/2 mv squared. Notice that both terms have an m in it, so we can cancel them out. Masses cancel out. It is not dependent on mass. The velocity is not dependent on mass at all. It's just dependent on, well, velocity is dependent on gravity, so the value for gravity. In our case, the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. That would change if you did this on the moon or Jupiter, but we have the height here, and that's in meters, okay? So v final of the slide is the square root of 2gh. If you look at the third kinematic equation, it actually is the conservation of energy, except sometimes we may have an initial velocity, but here we started off with 0. Okay, so note that this relates to the kinematics that we've done before, but we're analyzing it with energy concepts, and it's going to be more essential when we look at the rolling motion. All right, here we go. With rolling, same situation. We have gravitational potential energy to begin with, but no rolling, no kinetic linear energy, no rolling energy to begin with, because V naught is 0 here too. But then when you let it go, we now have this energy transforming itself into linear kinetic energy and rotational energy. Okay, well, how does that look in variables this time? Well, we begin with our mgh. We have linear kinetic energy, 1/2 mv squared. And the rotational energy term is 1/2 I omega final squared. Okay, notice that right now I cannot cancel these masses because this term doesn't have it, but we're going to work with it. We're going to work with it through some basic substitutions from the last slide, which had the relationships that we needed, knowing that we need to look up I. I for a solid cylinder is 1/2 mr squared. So that's this I over here. And notice it has the m in it. So therefore we're going to be good because these m's will cancel out, as you'll see. The omega is v over r, and of course we have omega final squared, and v final squared over r squared is what that becomes. All right, so now let's take a look at it. The m's cancel in all these terms. We still have 1/2 mv final squared from the linear kinetic energy, and now from rotational we have this. We have 1/2 times the I part, which is 1/2 mr squared. M canceled. And then we have the omega becoming v final squared over r squared. So now everything's in terms of v, which is great. The r squared here cancels with the r squared here, so it's not dependent on radius. The velocity actually, so you can have a really big puck or a very tiny puck. That doesn't really affect the rate of velocity that we'll achieve at the very end of the ramp, okay? So that's kind of counterintuitive. I think you would expect something bigger to maybe roll faster, but it turns out that a bigger object will probably just have a rolling frequency that's less. Like creating one rotation will take longer, but the actual velocity of the object will be the same as it's down the hill. So what we have over here, when we combine this term, 1/2 vf squared, and essentially this is 1/4. 1/2 times 1/2 is 1/4. We add them together, we get 3/4 vf squared is this gh naught, okay? So the final velocity for the rolling puck is the square root of 4/3 gh squared. I solved for vf, and this value is actually less than this value over here. So this one is less than that, which means that it takes a bit longer for the object to roll down the hill than slide down the hill. And that makes sense. In the activity where we compare different objects, spheres and rings and hollow rings, solid rings, cylinders of that nature, we know that they roll at different rates. We rank them, and by doing that, we recognize that because the energy is shared between linear and rotational, it's going to take a little longer to get down. The velocity is not as fast. And so we saw evidence of that. But now we can explain it because of the energy parts of it, that the energy is being shared by these two terms right there. So if I took a ratio of these two, V final slide over V final roll, it's about 1:2. So if there's no friction at all here and the puck slides downwards, the velocity will be 1.22 times faster than if a puck were then turn on edge and were to roll down this same hill. Have a little bit of friction though. You would need a little bit of friction to get the rolling going, the static friction, but it's the pure roll versus the pure slide. And so that's what it is. So here we go. It's Morad and that little Nini. Hey Nini. Okay, thank you. Let's see if she rolls. No, we won't do that. Okay, out.